So let's have a look at an example. So you might also be given a similar kind of description in your exam or in assignment number 2 as well. So you need to understand the program. So our favorite program runs in 10 seconds on computer A, which has a 2 gigahertz clock. So we are given the CPU time and a clock rate for computer A. And what we are trying to do is to help designer build computer B, which should run the same program in 6 seconds. Okay, but it has been determined that a substantial increase in the clock rate is possible on computer B. So you might also be wondering sometimes that why we cannot have a higher clock rate for every kind of processor. So if you have 2 processors, this discussion is separate from what you see on the slide now. So if you have 2 processors, A and B, one is running 3 gigahertz at 3 gigahertz speed, okay, while the other one is running, let's say, at 2 gigahertz. So can you imagine, like, ask yourself, why cannot we increase the speed of the other processor? Let's say computer A is running 3 gigahertz and computer B is running at 2 gigahertz. So can we just simply replace the clock on computer B and make it faster, as same as computer A? Can we do that? Why? Again, it depends on the hardware. If the hardware is designed in a way that it can process the data that fast, only then we can increase the clock rate. We cannot just by our own choice, I open my the 20 years old PC and put a new clock in it and it will start behaving faster. I cannot do that. Okay, so it depends on the hardware, which we have been discussing. Anyway, come back to this question. So to summarize, we have computer A running at 2 gigahertz clock with 10-second CPU time. What we need to do is to design computer B. And again, if you are given a task like this, you should also be extracting the important information and put it separately. Okay, this will help you solve the problem quicker. We need to design computer B. I have to aim for 6-second CPU time. We can do a faster clock, and it causes 1.2 times of clock cycles of A. We are just extracting the information from this description. What we need to do is to calculate how fast computer B's clock be. Okay, so we have only discussed one formula, which is this: CPU time equals clock cycles over clock rate. So what we can do is use this formula and apply it for the computer clock B, because we need to determine the clock rate for computer B. Okay, so we have been given clock cycles of B, which is 1.2 times of clock cycles of A, and CPU time of B is 6 seconds. It's already been given. Okay, how do we calculate this one? We do not know the clock cycles of A, but we do have this data available. Okay, so we can calculate the clock cycles of A with the help of this information: the CPU time times the clock rate, 2 gigahertz. Okay, you multiply this and put the same thing in here, 20 into 10 to the power 9 in the same formula, and then you got this value. The clock rate of computer B is 4 gigahertz. Okay, this is simple a word problem, and you just need to extract the information, apply the formula. So this is the first formula that you have studied, and it's pretty straightforward in calculating the performance, the clock rate of computer B. You have a question? Yeah.
So I know clock rate now answer the question how fast the computer clock be. So how about CPU time and then clock cycle? Like which question that component answer for?
CPU time?
Yeah.
For the computer B?
So if you have a question, you ask us, like, would it be like, oh, what the CPU CPU time of clock B, or are you gonna ask a different way?
It could be like here in this one, how fast must computer be clock be? So it's clearly ask you, where is the question? What clock rate should we tell the designer to target for computer B, of course. Okay, so clock rate is, again, we are looking for the frequency for the computer B. Okay, so frequency means you have to calculate clock rate, and you have this formula available. So you need to extract the information that is provided to you, and sometimes it is not straightforward. You need to apply it differently, just like here. For the case of computer B, you have been given CPU time and clock cycles. For computer A, you have been given CPU time and the clock rate. So that's why you are just applying the information that is provided to you. Okay. All right. And we can define the performance as the inverse of CPU time. Of course, when the CPU time decreases, we say that the performance increases. Okay, because it will be able to complete the task more faster. What if we have to compare the performance of two computers, the two processors? And this is a very very often task that we need to do. So let's say we say X is n times faster than Y. So this is how we calculate the performance. So n is the factor which defines which computer is faster by which factor. So let's say performance X divided by performance Y. So we have already seen performance is inverse to the CPU time. If you remember, I mentioned that CPU time is also referred as execution time, the time taken by a computer to execute the task. Okay, so I can use any of these terms. So if it is execution time, it is same as CPU time. Okay, so here we put the execution time here, and you solve it. So execution time Y or execution time X. So remember this rule of thumb. When you find out that one computer is faster than the other one, so this slower computer, you should put it on the numerator, okay, and the other one you put it on the denominator. So if you we will do the example next in the next slide. So when a computer is faster than, let's say X is faster than Y, then you put the execution time of Y on numerator. Okay, n can be less than 1. What does that mean? So n is defining the factor by which one computer is faster than the other. If n is less than 1, what does that mean? Slow. It's slower. Okay, so n could be 0.1, which means that one computer is 10 times slower than the other one. Okay, but when you follow this rule of thumb, n should always be greater than 1. So let's say we have a time taken to run a program is 10 seconds on processor A and 15 seconds on B. So the first thing you should ask yourself, which one is faster than the other one? So clearly A is faster than B. Then B means you have to put the execution time of B on top and the execution time of A at the bottom. Okay, so here, and then you find out how much the computer is faster. So A is 1.5 times faster than B. Okay, so these are very simple formulas so far, and all the formulae here are very simple, and we will see how you can use it. Now let's come to some real things. So you have written a program, something like this. So you need to determine the CPU time taken by this program. How can you determine the time taken by this program? In terms of the measure we have been using, the clock cycle. If I give you certain amount of tasks, and if I ask you how you can calculate the total time you take to complete the task, or total number of, again this is the example, total number of breath. Okay, so So how can you compute it? Number of tasks, right? So first of all, you need to determine how many number of instructions are executed in this program. So can you tell me how many number of instructions are going to execute in this program? You should be able to identify maybe a couple of seconds to check if it contains some instructions and a loop.
At least 403 or 103.
3? Okay, you're very close.
No.
Very close. Yeah. Come on. How many instructions will be executed in this program? Hmm?
230.
Halfway there. How did you calculate that figure?
The S2 is 100 and it's doing 2 instructions every time.
So S2 is 100, and which means that this loop is going to execute 100 times. And how many instructions are there in? How many instructions will be executing 100 times? There are 4 instructions in a loop which are going to execute 100 times. Okay? Yes.
404.
And these 3 first, before entering the loop, these are the 3 instructions that will be executed, right? So first 3, and then these 400 instructions, okay? Because 4 instructions in a loop, and the loop is running 100 times. So 400 plus 3, 403, and then 1 additional instruction will be executed. Which one is that?
BG.
They check again to check whether to run the loop again or not. Okay, so this is why there will be 3, 400, and the additional last instruction which is executed one more time to check whether the loop should be terminated or not. Okay, so there are 404 instructions. Now to determine these instructions, how much longer, how much time these instructions are taking to complete, how do you calculate in terms of clock cycles? How many clock cycles do they take? So what could be the formula? Like if I were to ask you how many clock cycles this one is taking,
Either the inverse of clock rate or the CPU time.
no, forget about the previous formula right now. It's just like in terms of clock cycles, you have like 404 instructions. Okay, in generally in any program, how many clock cycles a program would take? Isn't it the simple thing, like total number of instructions in a program times cycles taken by each instruction, cycle per instruction. Okay, if I give you like 10 tasks, and if I ask you how many breathing cycle you're taking to complete the task, so first of all the number of tasks matters, and then number of breath taken by each task. So do you think each task will be taking the same amount of cycles? Each instruction would be taking same amount of cycle? No. So cycles per instruction here has to be an average cycles per instruction, because okay, so first of all look at this formula, cycles per instruction. We can short it for CPI. The CPI equals clock cycles divided by instruction count, which is this, the number of instruction count, or we can write it like this also. So different instruction takes different number of cycles. For example, if you are performing an add operation where the processor needs to be inside the processing boundary, it does not need to go outside somewhere, right, to fetch the data from external memory. Okay, so the, let's say add operation will take 10 cycles, multiplication operation is more complex, it will take more cycles, and loading the data from memory is further complex thing in terms of memory, in terms of time, because it has to go outside the processor, fetch the data, and then put it in the register. So it takes more cycles. So whenever we talk about the cycles per instruction, we actually assume that we are calculating average cycles per instruction. Okay. So no matter we write CPI, it is always, now onwards it will be always be average CPI. Okay. So when you are given a task to determine the number of clock cycles taken by a program, you would always assume that you are given average cycles per instruction. Okay. So we have studied that we have two equations: CPU time, which is clock cycles time into number of clock cycles and clock cycle time, and we do have a formula for our clock cycle, so we can put this one into this one, so we get the new one. So you need to know what information is given to you, okay, and what formula you should be using. Again, I believe on focusing more on logically solving things rather than memorizing, so I will be providing all these formula. Okay, you do not need to memorize it.